I'm not going to go through the calculations, but if I would do something like NH3 plus HCl in a similar fashion to what we did before, we would start out with something that would be, in terms of pH, is going to be basic, and you're going to do that just like any equilibrium problem to find the pH of that weak base. Again, keeping in mind you're going to be finding an OH concentration, so therefore negative log of that is a POH. Subtract from 14 to get your pH at 25 Celsius. Then as we start adding HCl, there's going to be a point where there's not a lot of buffering going on. In terms of AP chemistry, no calculations there. If you had to do those, definitely quadratic formula. Here, given the magnitude of the Kb for ammonia in this case, you can still get by without the quadratic formula when 0 milliliters are added. And then once you get out here to the point where it starts to buffer, it's going to continue to drop as we add the HCl, but it's going to kind of level off because we're going to have a common ion. That common ion, in terms of stoichiometry, is the ammonium ion, and the ammonium ion is the conjugate acid of this weak base. So we got a weak base, and then we've got a conjugate acid of that. And again, that also makes a buffer solution. So this is going to continue to kind of drop, and then it's going to go through our equivalence point. At the equivalence point, here's what we're going to have. We're going to have ammonium chloride, if you want to think of it as a salt, but specifically this conjugate acid. That's all we're going to have at the equivalence point. So it's going to be acidic. This is going to be somewhere below a pH of 7 because we've got an acidic salt formed. And then once we get to excess HCl, same thing. H plus ion is going to be your predominant factor for your pH, and you'll just find its concentration, negative log of that. And it's going to drop to a relatively low value and somewhat level off pretty fast. So again, what would we have? Calculation here in the beginning, some calculations from here out to the point prior to reaching the equivalence point, where we're going to have a common ion. We're going to be able to ignore the plus and minus x, so the math will be a little simpler there. You don't need the quadratic formula. The only place you really have to have it is right in there. And then what happens here? Well, once we get to this point at the equivalence point, now all we're working with is that as an acid. So we would be doing an equilibrium expression looks like this. To find that H plus, to find how much of this we have, to find that pH. An appropriate indicator, something lower than 7, maybe methyl orange or methyl red, depending on the math, depending on the volumes and the molarity, but definitely something for an acidic salt. And then once we get to this point, it's just a matter of how much H plus divide by the new total volume and negative log that to get your pH. On the other hand, what happens if we do a weak acid with a weak base? Well, we still get kind of the same thing going on. Then we jump through an equivalence point, and then it kind of continues to go up like such. Long story short, we've kind of got the same math there that we have from there on out. And how do we do this? Well, the easy way to determine what that's going to be is we're going to look at the magnitude of the Ka for the weak acid and the Kb for the weak base to determine, is this salt going to be acidic or basic, given the magnitude of those. Of course, if they were the same, like ammonia and acetic acid, close enough to the same, then you get a pH of 7. But if the Kb is bigger, the bigger value, then it's going to be basic. If the Ka is bigger, then it's going to be acidic at that equivalence point. But you don't get away from doing equilibrium problems once you pass through that. So we're at equilibrium the whole way through if we do a titration like that. Normally don't see those on an AP exam in any quantitative form. You might see a qualitative question, but definitely no quantitative form. And the last thing I want to talk about here just real quick is titration curves for polyprotic acids. What we would get here if we started with the acid in this, again, we'd get a buffering solution, and we're going to get something that looks like that. Basically, this is the first equivalence point, and then the second, and then the third, because it's a polyprotic acid. So again, anytime you see some sort of a pH curve that has multiple equivalence points, that tells you that it's got multiple, in this case, multiple H pluses to be lost.